Again, welcome everyone to the University of Manchester's second new Turing Fellow Spotlights. So we have 50 new fellows starting in October. And we will have, this is the second round, so we will have more events scheduled in December and January and February next year. So it is my pleasure to introduce our first speaker, who is Professor Yu-wang Chen, who is a professor in decision sciences and business analytics at the Alliance Manchester Business School. And he will talk about decision analytics using data-driven modeling and evidential reasoning. So I would like to welcome Professor Chen to start his talk.
Thank you, Sophia. Let me share the screen. Just want to confirm you can see my screen. You can see my slides.
Yeah. That looks good.
Yeah.
Yeah, thank you. Okay, good afternoon, everyone. Thank you, Sophia, for the introduction. It's a pleasure for me to have this opportunity to present my research. So the title of my presentation today is Decision Analytics using Data-Driven Modeling and Evidential Reasoning. So this is the outline for my presentation. I will first introduce the context of my research, decision-making and uncertainty, multiple criteria of decision analysis, decision matrix over belief decision matrix. Then I will briefly introduce my methodological research on evidential reasoning and the belief rule-based systems. I will quickly go through a couple of research projects I'm working on or have completed in recent years, if I have time, before the final summary and the further research. So decision making is a part of everyone's life, and all of us have to make decisions every day, right from what we eat, what we do, to what research we are going to conduct. In our organization, decision-making can occur at all levels, from operational to managerial to strategic. However, it was reported by IBM Analytics back to a few years ago, 1/3 business leaders frequently make decisions based on information they do not trust or don't have. More than half of the CEOs need to do a better job capturing and understanding information in order to make informed decision in businesses. So data-driven decision-making is regarded as a fundamental to improve the situation of decision-making in practice. So decision analytics is mainly concerned with use structured, quantitative, and analytical approaches to promote data-driven and evidence decision-making in business and management. So decision analytics can be seen as an integrated decision-making process with the use of both knowledge-based and data-based, say intelligence. Knowledge-based intelligence from decision-makers and experts, computational intelligence from machine learning and AI models. So the end of the knowledge-based decision-making, this side, so decision-making, the very end, decision-maker guesses without prior experience. But very often, decision-maker use prior knowledge and judgments in the decision-making process. So knowledge-based intelligence involves something like, say, decision rules, case-based reasoning, based in inference. Of course, human biases and bounded rationality are very common in knowledge-based decision-making. The other side, machine learning and AI models can be developed purely based on data or predominantly based on data. But of course, a pragmatic understanding of the decision context is important in order to make use of machine learning and AI models in decision support. Also, computational intelligence can inherit human biases in their decision-making process. So decision analytics aims to combine knowledge-based intelligence and data-driven intelligence together to support data-driven and evidence-based decision-making. What is decision-making? If we look at a simple case study in our teaching for MSc or for undergraduate students, we assume, okay, we have 3 alternatives to invest in a real estate market, basically apartment, office, or warehouse. The annual return and the different economic situation for each alternative can be estimated using data, historic data, for example. So we can estimate the potential returns for all combinations of decisions and the states of the nature, basically the future economic situation in this case. So we have this data, and which property are you going to buy? That's a decision-making problem. Of course, if it is for sure the economic situation will become better next year, there's no issue at all in decision-making, right? We pick up, say, this option, which gives the highest return. But very often we have to make decisions under uncertainty. We are not very sure what will happen in the future. So the future is uncertain. So we consider decision-making under uncertainty. So uncertainty can be associated with partial knowledge, uncertain information, unknown future, etc. So the simple decision-making problem already involves different considerations. There are even more challenges in applying decision analytics in real-world scenario. For example, for risk analysis in containerized supply chain, for example, from Liverpool to Shanghai. So we have to consider different types of risks. And in order to assess the risks comprehensively, both quantitative data and the quantitative information need to be connected from different sources in order to produce the risk matrix. In consumer preference modeling for new product development, also data and information should be connected from different sources. Also, the data can be in different forms with different skills. For performance modeling and the decision analysis of renewable energies, and very often a hierarchical decision model can be developed. In this hierarchical structure, as you can see from these, say, diagrams, and say the environmental impact can be assessed against different sub-criteria. So basically, we consider a set of decision criteria in our hierarchical structure. In multiple criteria decision analysis, we can often construct a decision matrix to support decision analysis. In this decision matrix, each element, such as A11, represents the average assessment of alternative 1 over attribute or, say, criteria, or, say, basically variable 1. Often, average numbers are used to assess each alternative on decision criteria. However, it's important to bear in mind that the same average number can be associated with different distributions. For these two continuous distributions, the average is the same. For these two discrete distributions for quality assessment, the average is also the same. Although the average is the same, but the distributions capture different types of information. So it means the flow of averages can distort everyday decision making in many areas. So simply speaking, the purpose of multiple criteria decision analysis to support the decision making process of identifying the most preferred solution from a set of efficient solutions. If there are only 2 criteria, for example, safety and profit in this small case, both for maximization, we can visualize the decision-making process. So we have different alternatives in this small case. Obviously, the alternative C, basically D and E are better than C on both criteria. So C is a dominated solution in this case. And D and E is better than D on safety while have the same profit. So D to some extent is also dominated or is a weak efficient solution. Theoretically, we can identify all efficient solutions, we can identify the efficient frontier. As a rational decision maker, we always pick up alternatives on the efficient frontier. This case only involves two criteria. If there are more than two criteria, of course, we have to find a way of aggregating information from the criteria to the top level, the decision outcome, such as using the simple weighted sum. So back to the law of averages I discussed previously. In the research conducted by myself and some colleagues in the Decision and Cognitive Sciences Research Center in the Business School, we propose to extend the decision matrix to belief decision matrix. In this belief decision matrix, we use a discrete distribution to capture assessment information for some criteria. So the discrete distribution can represent, of course, the precise numbers. It can also present uncertain information, like probability distributions. Also uncertain judgments, even with ignorance. So in the past year, my research focuses mainly on multiple criteria decision analysis, using information from different sources. We consider information representation, inference, and data analytics. So here is a small web search cluster analysis to the titles of my publications I published in the past decade. So the keywords for my publications include belief rule-based models, evidential reasoning, also decision making, prediction, analysis, network, and so on. In decision theory, evidential reasoning has been developed as a generic evidence-based multiple criteria decision analysis approach for formulating decision-making problems, aggregating information from the bottom level criteria to the top level decision outcome, also capture information in different types in order to support decision making. So the idea is very straightforward. We combine information from decision criteria together in order to support the final decision outcome. And mathematically, evidential reasoning is a generalized probabilistic inference which extends the density rule and a Bayesian inference. So furthermore, in the past decade, I've been working on combining knowledge base with an evidential reasoning method. So as you can see from this small diagram, so on one side, I explore how to formulate different types of information in the decision-making process, including quantitative information, quantitative data, probability distributions, and then further extend the knowledge base to multiple levels. So we consider a hierarchical decision-making process as well. A simple comparison between the belief rule and the traditional if-then rule, as you can see, for the belief rule, the consequent part is a discrete distribution. We use a belief distribution to capture the uncertain outcome. In this case, the traditional if-then rules are special case of belief rules. Probability distributions are also special case of belief structures. So it means we can use a small number of belief rules to capture relationship in a more accurate way. We can also use data to train the parameters for the belief rule base. A genetic form of belief rules can be formulated like this. We can use this to capture uncertain decision outcomes. So the decision outcomes can be subjective in evaluation grades or numerical data or different events or different faults in fault diagnosis. A single layer belief rule-based model, something like this. So this can represent a transparent and interpretable inference process from input information to the decision outcome, which is represented by a belief distribution. On the other side, I have been working on different inference mechanisms, including the classic depth-central theory of evidence to evidential reasoning, also some other reasoning models in order to combine information together. So the methodology can be formulated mathematically by the belief rule-based matrix, something like this, and then we can say formulate the whole model using the mathematical form within constraints or parameters. Also, the input and the outputs can be represented by belief distributions. We combine these two sides and the knowledge-based inference engine together, and the whole model represents a belief rule-based inference methodology using evidential reasoning. As the output is represented by the distribution, so we can easily capture uncertain outputs in decision analysis, something like the minimum, maximum, or average utilities in decision analysis. We can further use data to train the models. The initial belief rules can be constructed using expert knowledge or historical data. We can further use the data to train the parameter in order to make the model more accurate. Okay. So next, I'm going to provide a very brief overview of 3 projects. Basically, say 2 of them I completed in the past years, and say the last one basically is an ongoing project. So the first project is about the containerized supply chain risk analysis. Of course, containerized supply chain plays a very important role in global economic prosperity. Approximately 90% of world trade is achieved in shipping, say, containers. So in this project, we evaluate and prioritize different types of risks for mitigation strategies. So we consider the physical flow for the whole supply chain, say from supplier side to import side. At each stage of this whole supply chain, we have to consider different types of risks. Like maritime transportation, we have to consider risk like say fire and explosion, collision, and these type of risks. So data needed to be connected basically from different sources, from experts, from historical records, in order to evaluate these risks. And then we combine information together in order to prioritize the risks for mitigation strategies. So we used the methods we developed, say including evidential reasoning and belief rule-based models. So the second project basically is to formulate a relationship between product profile and the customer rating in new product development. So in this case, data are also collected from different sources, from panelists, also from say consumers, from surveys, also from experiments. It is worth mentioning that the target for prediction for this project is actually distributed customer liking, not a number, because customers can have very divided preferences for some projects. So we do not predict the average consumer liking, we predict the distribution. So typical machine learning models cannot be used directly for this distributed distribution. As we discussed previously, we use basically a belief structure to capture the output for our model. So we can capture this distributed customer liking for this project. So the third project basically is an ongoing KTP knowledge transfer project with a forensic testing company. So the main focus of this project is to use data from different sources, including analytical testing data from human samples, expert rules, questionnaires from drug users for substance misuse assessment. So we use data in different forms and also in different scales in order to support decision making in the court. So we also use a set of different machine learning models plus rule-based models to predict the drug usage for certain patients or clients in this case. Okay, so in this short presentation, I briefly talk about my methodological research and also a couple of research projects in the context of decision analytics. In recent years, I focus a bit more on analyzing and formulating social influence decision making, including voluntary decision, say vaccination decision making in the current context. So we aim to combine social network analysis together with a multiple characterized analysis. We also focus a bit more on using data science, AI models in decision support and analytics. I would be very interested in, say, wider research collaboration and also more applications of data and decision analytics in different areas. Thank you very much.
Thank you very much, Yu-wang, for keeping the time as well. So we have about actually 7 minutes for questions. I would like to open the floor. Thank you. So any questions? Questions? So I'll ask a question because I come from a different field and I'm working also on uncertainty, but from textual points of view. So my question is, you mentioned about qualitative and quantitative data. To what extent, I mean, how do you envisage any problems when you're trying to integrate different types of data to detect the decision making? What are the challenges, the main challenges?
Yeah, this is a very good question. Thank you, Sophia. Let me just put the question in a context. So basically, the first project I introduced. So for this project, basically, in order to prioritize risks for mitigation, because resources and money are always limited, so we cannot mitigate all the risks in containerized supply chain. So in this case, basically we collected data and say one source quantitative data. We know, like say a fire explosion condition, how many times they happened in the past for certain say supply chain company, or say for certain new report. So quantitative data and frequency analysis, something like that. On the other hand, say we also collect data from experts or say managers or say staff for a containership. So basically, they provide say subjective data, like say from 2 dimensions. The likelihood, how likely you think say fire will may happen in a containership. So they provide different subjective evaluation grades and also the potential consequence in case a fire happens in a containership. What mitigation strategies you have, and say what would be the potential consequence? Because the potential consequence before say something happened, we don't know the potential consequence. So that data, the potential consequence, is also evaluated by experts. So in this case, we have to combine quantitative data and the judgments, say prior knowledge from experts together, in order to produce a ranking of different say risks. So basically, in that case, say the main challenge was that we decide the relative importance of different say information sources, and also how to combine these 2 different types of information together. That was the main challenge for this say particular research.
So yeah, that's very interesting. So I mean, any other questions? We have 4 minutes. Okay, I'll ask another one because nobody is asking. Maybe it's any questions. It's good to have a discussion. So again, this has to do with the priors that you are using in the different knowledge sources. In a kind of belief, if you have a kind of belief and system, I mean, to what extent you're using existing knowledge sources as priors, and what kind of difficulties you're encountering? Again, this is a very insightful question. And say in belief rule-based models, it's pretty hard to create the initial rules, because compared with the traditional rules, we have the uncertain outputs here. Let me say more to this. And this one. So we have a number of the different say parameters, like the relative importance of different rules, and also the relative importance of different inputs, and also the belief degrees.
which are associated with different outcomes. So normally we can say, in the first instance, we can formulate rules from experts, like a risk assessment. We can collate information from experts, say construct the initial rules. And then we can also say generate rules randomly, or we generate rules from data. And once we have more, say, data samples, we can further train the parameters and make the rule, say, basically more useful or more accurate in capturing relationship. So rule-based model, in my understanding, essentially we consider different scenarios for the whole input space. We decompose the whole input space to smaller, say, areas, and then we consider local knowledge within a small area. That's the idea, yeah.
Okay, thank you so much. A couple of minutes if there is any other question. Well, if not, I would like to thank the speaker for a very nice talk, an excellent talk. Thank you again for your time. So it's time now to introduce our second speaker for today's event. And this is Matthew Thorpe, Matt Thorpe, who is a senior lecturer in applied mathematics, who is going to be talking to us about large data limits in semi-supervised learning. So looking forward to this. Thank you.
Okay, thank you very much. I actually slightly extended the scope of my talk to include some other work as well, but it's kind of mostly focused on large data limits. Oh, okay, right. Okay, so I guess just to kind of introduce myself. So actually, I'm a lecturer, not a senior lecturer in applied mathematics, but thank you for the promotion. So I previously was a research fellow in Cambridge, which actually is where I'm at the moment. I'm attending the Mathematics of Deep Learning program here at the Isaac Newton Institute. Before that, I did a postdoc in the US at Carnegie Mellon University, and my PhD originally comes from the University of Warwick. So sort of broadly speaking, I kind of have sort of three areas of interest. So I'm interested in discrete to continuum variational limits in sort of graph-based learning. I'm interested in graph neural networks, and particularly kind of the connections with sort of PDEs. And I'm interested in sort of optimal transport type distances. And of course, I'm interested in all the sort of applications that come along with all these areas. Okay, so I've kind of written down a few of the projects I've been involved in recently. The ones highlighted in red are the ones I want to kind of touch on today. So I mean, typically, the large data limit graph-based learning. So we set up some sort of variational problem on a graph, and then we're looking at what happens as the number of nodes in that graph goes off to infinity. And this is in sort of a variety of contexts. So it could be sort of semi-supervised learning, it could be clustering, it could be fully sort of fully supervised, and and the applications could be more geared towards imaging, or a range of scenarios. In neural networks, I'm kind of interested in what happens as you get sort of deeper networks. So in particular, making the connections between a sort of a very deep network and something like an ODE system, and trying to use this to design sort of new architectures. So more recently, I've been trying to kind of combine this with this sort of graph-based learning to design sort of graph-based neural network schemes. Getting and finding sort of optimal transport. This is something that maybe you've never heard this before, maybe you know a lot about this. If you've never heard this before, this is just a way of defining distance, which is particularly sort of useful in imaging. There's a few disadvantages, but we can kind of find our way, circumnavigate these disadvantages. And okay, there's some sort of very nice sort of application. So an application I won't talk about is something like COVID-19 classification on X-rays. Okay, so part one is kind of this graph-based learning. Okay, so at a high level, what do we have? So we have a set of feature vectors. So these live in some Euclidean space. And we have a subset of labels. Okay, and the aim is to try and find labels for the unlabeled feature vectors. Okay, so we do this in a graph-based setting, which gives us like a geometry. Okay, so the graph consists of nodes, which are just the feature vectors, and then the weights are some measure of similarity between feature vectors. Okay, so we sort of say, okay, the weight is very big if we think of xi and xj as being very similar, or the weight's approximately 0 if it's very dissimilar. Okay, so we're given these sort of labels. So I've just assumed that the first m feature vectors are labeled. Okay, and I'm going to assume that they're sort of categorical labels. So we have k different classes, and we want to put each feature vector in one of these k classes. So the assumption then is that these feature vectors should have similar labels, which of course is very reasonable. Okay, so the problem is we're given our feature vectors, we're given a subset of labels, and we want to find the best function that sort of agrees with the labels, and then we'll use that to predict what label we should give the unlabeled feature vectors. Okay, so the classical kind of approach for this would be to do something like regression, right? So one would look at minimizing the gradient subject to this constraint. So, because this isn't really taking advantage of the fact that this is a semi-supervised learning problem. So this is kind of a very nice example by one of my collaborators. So let's imagine we have only two labels. We have a red label and we have a blue label. And now I want to divide my state space up into these regions. So of course, like the most natural thing to do is just to put a line down the middle. Anything to the left is red, anything to the right is blue. Now you give me unlabeled feature vectors, right? And you can see if I apply this decision rule, it's not really a very good solution, right? So I haven't learned my geometry. So a much better rule would be to move the line over here, and then okay, you can see this is probably a much better answer. Okay, so this is kind of what the semi-supervised learning setting, philosophically, what we kind of hope to take advantage of. Okay, so mathematically, the way we sort of do this is to look at minimizing an energy. So the energy we look at minimizing is the following. So we're looking for the function fn, which, okay, so we define this energy as being the pairwise difference to some pth power weighted by the edge weights. So what this says is if we're looking at minimizing this energy, then if two feature vectors xi and xj are similar, that will mean that wij has to be very big. So this means then that fnxi minus fnxj should be very small. So in some sense, we're encoding smoothness. Okay, so this is the variational problem, which I'll talk about for a little bit. Okay, and so then we get to the actual classification by just looking at the looking at the label that's closest to the function fn, so just thresholding. I'll try and sort of skip over this a little bit because I don't want to go too much into the mathematics. But essentially, if one scales this energy the right way, and if one scales the edge weights in the right way, one gets a kind of a continuum model which depends on the density of the data. Okay, and there's some various sort of assumptions that one needs. So one has to scale the graph so that the graph stays connected. But these kind of all to get sort of technical details. Okay, there's some maths on this page, but I think it's quite interesting to go over, and it perhaps gives you something that you wouldn't necessarily expect, particularly maybe from mathematicians. So one thing you can look at is that if you want to minimize this energy here on a continuum domain, well, there's various sort of regularity results, which essentially mean that if P is sufficiently big, so this means bigger than the dimension of the space, then F has to be continuous, and it makes sense to have point-wise constraints. When P is not very big, you can have discontinuities. If you have discontinuities, it kind of means if you only have finitely many constraints or finitely many labels, then you essentially it's not a well-posed problem. Okay, and one would then expect that P being bigger than D is kind of enough. It turns out this isn't correct, and we can kind of see this through like a very simple example. So if I say, let's say we have to label 1 on the first feature vector and label sort of 0 everywhere else. So this is kind of a spike. So this is kind of a bad thing, right? Because it means that we're not very smooth. We're not sort of interpolating between our feature vectors very well. So this should have very high energy. Once we kind of put this into our energy, essentially, just to kind of cut to the chase, what we actually find is that this energy can go to 0 if epsilon is too big. Right, so this kind of means there's a sort of nice interplay between the sort of the scaling on the graph and whether or not we get a sort of like a smooth interpolation between labels. Okay, and this is, you know, I'll just flash this theorem up. Essentially, this theorem is kind of sharp, and it gives the two regimes where we either are in a well-posed regime if our sort of scaling in the graph is not too big, and we're in this sort of ill-posed regime if the scaling in the graph is too big. Okay, to kind of show you what's going on. So this is an example where we only have two labels. So we have a label up here and we have a label up here, and we've chosen, okay, P equals 4 in our energy, and we've worked out what the continuum kind of minimizer is, and we get this sort of nice you know, smooth sort of interpolation between the two labels. Okay, so here I've done the same thing, but now I've done this with data points. So this is, you know, around about 1,000 data points, and you can see, you know, these two, you know, you can kind of believe that this finite data problem is kind of approximating this continuum data problem. And this is weird. So epsilon is the scaling on the graph. This is a scaling on the graph that's fairly small. If I increase my sort of scaling, if I increase my epsilon, so I sort of look at sort of essentially my graph connectivity becomes bigger and bigger, and I zoom in to sort of around where one of these constraints are, what you can see is you get increasingly you get kind of more discontinuous. So your function gets less smooth, and this kind of really shows you how you're going from kind of like a well-posed case over here to like an ill-posed case over here. Okay, so this is bad. So how do we sort it out? So there's kind of two things we can do. So one thing is we can increase the number of labels that we have. So everything I kind of showed you before is true for when you fix the number of labels, but you take the number of unlabeled points after infinity. And what we can show is that if one has at least this many labels, then you should be in a well-posed regime and you're okay, right? So your labeling sort of function is going to be sort of nice and smooth. The second thing you can do is look at correcting the bias. So once you come to like thresholding, so you can see here like an extreme case where this is the minimizer for a particular problem where we've essentially got, you know, a spike here, which one of the constraints is a spike here satisfying the other constraint, because what we would actually do in practice is we would threshold. So you can see if we threshold through one of the spikes, then basically everything gets associated to one label, not the other. But if we can kind of make sure that this plane is in the right place, then maybe we have some hope. And actually this sort of idea led to kind of an algorithm which we call Poisson learning. And this actually had much better results. And this essentially was just from correcting the bias that we got from the previous problem. So I can kind of, you know, show you some results, and of course, you know, these results all work very well. So the class learning, this is the kind of the original problem which I showed you, and we're looking at, so this is the MNIST data set, which is essentially a toy data set. We're looking at one label per class. There are 10 classes because the MNIST data set is handwritten digits, 1 to 10. So on a data set with one class, the class learning gets about 16% accuracy. So chance will be 10% accuracy. So it does slightly better than chance, but not much better, right? On the other hand, just correcting for the bias, right, this brings you already up to about 90% accuracy, right? So, and of course, you know, we compared with a whole range of other sort of semi-supervised learning algorithms, and, you know, you can see we beat them all as long as we, you know, in the regime where we have very few labels. So, you know, only sort of, you know, well, 50 labels per class is the most we did. Similar story in other data sets. So there's the fashion MNIST data set, WebKB. These are kind of considered slightly harder problems. And it's kind of the same story that, you know, our corrected bias algorithm does, in most cases, significantly better. You'll notice, of course, as you get more and more labels, the gap closes. And this is really because our algorithm is kind of designed for the low labeling rate regime. Okay, so I went through that very quickly. Okay, this now onto this kind of second part. This is kind of the optimal transport part. So first of all, I kind of want to motivate optimal transport. So let's say we want to compare the distance between two images, and my images are a red ball and a blue ball. So the first thing you can probably do is think, well, let's use like a Euclidean type distance. So in a Euclidean type distance, you take one image, you put the other image over the top of it, and you just subtract them. Okay, and then you look at, you know, what's the, essentially in this case, what's the area left. So of course, between these two balls here, right, the Euclidean distance between the two balls is just going to be, you know, the red area plus the blue area. Okay, so this is maybe okay when the balls are overlapping, but you can kind of see once the balls have moved apart, then the Euclidean distance is going to be constant. It's just going to be twice the volume of the balls. And in particular, there's no gradient. So if we want to optimize this, say we want to move the blue ball in the direction of the red ball, well, we have zero gradient. So no gradient descent method is going to work in this sort of Euclidean setting. A more sort of physically accurate model is kind of the Lagrangian viewpoint. So the Lagrangian viewpoint says, okay, how far do we have to move the blue ball to get to the red ball? So in this case, of course, right, how we move will be to sort of shift everything to the left. Okay, and then so the Lagrangian distance, or this will be the optimal transport distance, is going to be the cost of essentially this vector field which pushes forwards the blue ball into the red ball. Okay, so I mean, I won't just spend too long explaining kind of, you know, what the Wasserstein distance is, but essentially it's the picture on the previous slide. So if we have, now our images are going to be measures, so maybe we have a measure mu and we have a measure nu, and then we have some map t which deforms mu into nu. Okay, so this notation here just means that mu is rearranged and now it's the measure nu. And then we look at paying the cost of transporting from x to t of x. Okay, and so you think of this as, you know, we want to move mass mu of x from x to t of x, and the cost we pay is proportional to the squared distance. Okay, so this is kind of very nice. So as you can see from the previous slide, you know, we kind of have, you know, it's a Lagrangian model, which is often more physically reasonable. It's fairly actually simple to understand kind of what's actually going on, even if the mathematics kind of hides this a little bit. One can think of this as just moving, well, this distance was first proposed by Monge, who kind of did this in the context of moving dirt from a trench to a wall. So he wanted to know, if I dig a hole and I want to build a wall, where should I move the dirt from my hole to the wall? So this, I think, gives it kind of like makes it kind of easier to understand than other types of Lagrangian distance, which are slightly more obscure, in my opinion. There's lots of nice theory behind this, which makes it desirable. So, you know, this actually is a metric. We have geodesics, we have a Riemannian structure, which I'll touch on later, and there's sort of nice theoretical and characterizing properties. So we know things like, you know, when there exists a map T, we can characterize this T under appropriate conditions. Okay. I thought there was going to be a slide in between this, which kind of led to the disadvantages. Let me just check if there is. Okay, I unfortunately seem to have cut the disadvantages off, but let me sort of do this ad lib. There's potentially two disadvantages to this type of distance. The first is actually it's quite slow to compute numerically, because defining this t is you know, it's an optimization problem. Although it's convex, it's actually not so easy. Well, it's convex in an appropriate formulation. The second thing is that we have a lot of sort of off-the-shelf data analysis tools. So I'm thinking of things like principal component analysis, linear discriminant analysis, but these are all for Euclidean distances. The question is, well, how can we do this in the sort of Wasserstein topology? And this, of course, is much harder. So what I want to talk about now is kind of how to linearize these distances. So the point of linearizing these distances is essentially to find an embedding so that the Euclidean distance in the embedded space is approximately equal to the Wasserstein distance in the original space. So how you can kind of think of this is, you think of this as, okay, we start off on this Wasserstein manifold. Okay, so this is some sort of, you know, curved space. So here we have, three measures, mu, nu1, and nu2. And then we have the Wasserstein distance, which is just the length of this curve along the manifold between mu and nu1. Okay, and the green curve is the Wasserstein distance between nu1 and nu2. Okay, and likewise for the blue. What we can do is we can project onto the tangent space. So the tangent space is down here. And the idea is, so mu is projected to this I0 tilde, nu1 is projected to I1 tilde, nu2 is to I2 tilde. And the idea now is that if we do this projection, well, the length of this red curve here in the Wasserstein space is exactly equal to the Euclidean distance in the tangent space. Similarly for the blue curve here, so the blue curve here is exactly equal to the blue line here. And then kind of approximately, we expect that the green curve here is going to be equal to the green line here. And this sort of depends on how curved the space is, but it's kind of an approximation we can make. Okay, so more precisely, the Wasserstein distance between a measure mu and nu is actually equal to the Euclidean distance, okay, which is given by this L2 norm, of the logarithmic map, which is just a projection into the tangent plane. Okay, so this kind of allows us to kind of define a linear Wasserstein distance. Okay, so the linear Wasserstein distance is just the distance between the two, between the distance in the tangent space, essentially. Okay, and the kind of the approximation is that if we take two arbitrary measures, mu1 and mu2, then this should be approximately equal to the linear Wasserstein distance at some center mu. Right, so this approximation here is just saying that this green curve here should be approximately equal to this green line here. Okay, so this framework now allows us to do things in Euclidean spaces, and so this is kind of one little example of how we can generate new images in using the Wasserstein topology. Okay, so we start off with a data set of images. So first thing is we're going to do is we're going to try and approximate this manifold at k points. Okay, so we have n images. So we do this linear embedding around some point, and then this now gives us a big sort of well, a lot of vectors in some Euclidean space, and then we do something like k-means. Right, so k-means now gives us our k points at which we can try and approximate this manifold. Then we do the same thing. So at each of these sort of k centers, we look to linearize again around these points here. And now what we do is we fit a Gaussian to it. So okay, so here we kind of imagine is our linearization around this, okay, the second data, well, the second cluster center here. Now, okay, if we want to generate a new image, what we do is, first of all, we sample one of these cluster centers. Then we can sample a point in the linear space, and then this whole process is reversible. So we can go back and we can generate a new image. So I think a question whenever you're looking at the data generation is, are you really generating new images, or are you just sort of pushing back what you had before? So we did this with a very, very, very small number of images. So we did this with a data set of just 19 images. So the top row here are the images which we used, and then the second two rows, these are the generated images. And what you can kind of see is that actually, none of these faces here appear exactly in the top row. So we are generating new images. I mean, of course, it's not perfect, right? You can see just around here, the mouse is kind of messed up, but we're also only learning from 19 images, right? I mean, it's a difficult problem. Okay, I can give you sort of an example of like a sort of a toy problem. Okay, so this is a data set, obviously synthetic, and it has sort of two modes of variation. So one mode of variation, which actually isn't so clear on these pictures, is that one of these sort of ellipses has more mass than the other, and it changes from one end to the other end. So I can't remember now which one it is, because it's not so clear actually. The other mode of variation is the orientation of the ellipses. So you can see here, it's neg on its side, here it's standing up. You can kind of just ignore these are two different types of optimal transport distance. This is the Wasserstein, okay, it's the Wasserstein center. This is a slightly modified version known as the Hellinger-Kantorowicz distance. Okay, and we can from this, we can look at, so we do our linear embedding, and then we can look at what are the modes of variation in this data set. So let's focus on the HK embedding. What we find is that there are two, for PCA, this corresponds to two modes, the first two principal components corresponds to two types of deformations. So the first principal component corresponds to stretching the top ellipse and sort of squashing the bottom ellipse, right? And that's exactly kind of what one of the modes of variation was in the data set. The second mode of variation corresponds to enlarging the first ellipse and shrinking the second ellipse. So again, this is exactly what we get. So it's kind of nice, right, that this that we've kind of really captured the geometry. Even though it's a synthetic data set, we've kind of managed to find it. And of course, Euclidean distance wouldn't capture this sort of thing. So we applied this to the problem of tagging jets from, again, so this is actually from a simulated data set of particle collider events, but it's meant to be fairly realistic. So we're given sort of QCD jets and W boson jets. So the if you just focus on the sort of green dots, right? This is so somehow that this is meant to represent the back plate, and then we have particles hitting the back plate, and then the idea is, okay, what reaction did these particles come from? Okay, so we have, so the QCD jets, so typically you get sort of like one big particle in the middle and then sort of other smaller particles around them. In the W boson jets, you typically see sort of two big jets in the middle and then surrounded by sort of smaller particles. Again, we can do this sort of linear embedding space, it's just linear embedding, and then we can sort of look at the geometry. And again, it kind of tells you something about what's sort of going on. So what you can sort of see here is that, sorry, to get which way around it is. So I think the brown here is 2. So the brown, it corresponds to the W boson jets. So you can sort of see that we do get, the W boson jets are kind of accumulating around here, and the QC jets are accumulating around here. So you see, you also get some of the, I forgot which way around it is again, of the W boson jets over here. But actually, if you look at that, so even though, so 6 is a W boson jet, but actually it does kind of look more like a QCD jet, because it is kind of, there is only kind of one particle. So it's kind of reasonable that our sort of algorithm would sort of struggle to distinguish that from the other QCD jets. Okay, so now once we're in this linear space, we can apply sort of off-the-shelf tools like linear discriminant analysis, k-nearest neighbors, support vector machines. Okay, and so of course, we get sort of fairly reasonable results. So these are length scales which I haven't really introduced, but essentially we can kind of control how far this transport happens. Okay, so I'll just sort of summarize very quickly. So in part 1, we looked at how to scale graphs in order to achieve sort of asymptotic well-posedness. And we found that there were regimes where the problem is ill-posed, and then we kind of proposed those 2 solutions. So one is to just increase the number of labels, and we can find a minimal number of labels from these. And the second is to try and correct the bias, and this led to kind of a new method, which is very good at lower label rates. In the second part, we looked at linearizing this optimal transport framework, and this was to allow for off-the-shelf data analysis tools in this sort of better geometry. Okay, and we've looked at sort of several examples, so including sort of data generation and jet tagging, and we're looking at sort of more interesting, other applications, including sort of designing fingerprints for material sciences and sort of medical imaging. So these kind of parts are more in progress. So with that, thank you very much, and yeah, any questions?
Thank you very much, Matt, for a very interesting talk. We have actually 3 minutes for questions, and the floor is open. Any questions? Okay, I'll I'll ask a question again. So a bit outside my area, but somehow you mentioned on your image generation, you mentioned that you had. I mean, I was just wondering about the scalability of your. Yeah, when the previous one, when you're generating images. So you mentioned that, about learning new images, and you had only a small amount of original images to generate, and some of them, the generation looks quite different. So, I mean, what is the impact if you had, did you try it on a largest data set to see how this would be different if you have more images to learn from?
Yes, that's a good question. So I guess maybe there's two ways to answer this. So I guess the first thing actually is one of the reasons for doing this sort of linear embedding actually is precisely so you can deal with bigger data sets. So one problem, if you wanted to do, say you wanted to do everything in the Wasserstein space, and then you wanted to compute all pairwise distances, say, that's very expensive, right? This is n squared times, however long it takes to compute a Wasserstein distance, which can be, fairly significant. On the other hand, this sort of linear embedding space, you have to do the embedding, which is essentially equivalent to computing the Wasserstein distance sort of once. So this means you have to do it sort of n times for a data set size n, and then you do everything in Euclidean space. After that, everything is kind of very quick. So of course, you can't go to arbitrarily big data sets still because, it is still expensive to compute each embedding, but you can go much bigger than you can do just doing this in the Wasserstein space. So I guess that's one thing. But I guess you can also ask this, well, do we get better results if we do for bigger data sets? It's a good question, actually. I'm not sure if this paper was from 2018. I can't remember now which experiments went in it. I think we do have more experiments, but I can't remember now if we have kind of like a large scale experiment. I would certainly expect to do better because essentially, we're trying to learn these tangent planes here. And so of course, the more data you get, kind of the better you kind of approximate these. So these tangent planes are all kind of, they're estimated using a Gaussian. So of course, one expects better results if you get more data, but I don't actually remember if we did that experiment or not.
That's okay. We have, I know it's 3 o'clock, but you have a couple of interesting questions. So the first one was if there were any disadvantages to a Poisson learning. Actually, that's a good question. I wanted to know too. Yeah.
So we didn't really test this when you get high label rates. So this could be one. So I don't know. So this may not be a disadvantage, may not be an advantage. What we kind of notice is that the gain sort of disappears as you get to higher label rates, which is what we expect because we only corrected this bias in the low labeling rate regime. I guess in terms of numerical sort of performance, like the original algorithm essentially is pretty quick, especially when the data set isn't too big, because you have analytical solutions for it. So, I mean, you have to invert a matrix, but essentially you don't need to do anything. You don't have to have any optimization algorithm. For Poisson learning, it's not so simple, right? We actually have to do some sort of gradient descent. So, potentially it's a bit slower there, but we find it's not too bad.
Okay, and the last one, so people can leave if they want, is about the GNNs. This is from Julia. If we are looking at the impact of the graph structure on learning as well.
I'm not 100% sure what the question means, actually. So in terms of graph neural networks, again, we're kind of interested in this sort of semi-supervised learning regime. Well, we're interested in two things. Like one is looking at deep graph neural networks. So there's kind of, I would say a fair amount of excitement where this group, kind of a lot of the graph neural networks are sort of based around diffusion equations. And the problem with the diffusion equation is that it diffuses. So what you have this sort of over smoothing problem that as you go through your network, everything kind of becomes more and more constant, and it kind of, no one's really as far as I'm aware, been able to get sort of graph neural networks to work at very deep layers. So the idea is to kind of use some of these sort of insights from what happens in, in past learning and Poisson learning to design sort of new sort of architectures which will work for deep layers. Now, I have to sort of admit, I guess in machine learning, it's always deeper is better. If you asked me to kind of justify that, I don't know if I could, right? I'm getting on the bandwagon and going going along with this, but yeah.
Okay, thanks very much. Actually, we're running a bit out of time, but we started at past 3, so we're exactly 1 hour. With that, thank you very much to both our speakers for excellent talks. And please, we have another series, the third in December, and we'll advertise that as well. So again, thank you very much for your time. Bye-bye.